Dear students, welcome to the chemistry class under paper 1. Okay, so today we'll go through chelates. So in the previous sem you are well familiar with polydentate ligands. Say bidentate, tridentate, tetradentate or hexadentate ligands. You are knowing it. So bidentate ligand is the one which is having two lone pair of electrons. For example, oxalate or ethylene diamine. So it is a ligand which is capable of donating two pair of electrons to the same metal ion, isn't it? So hexadentate, well-known example is ethylene diamine tetraestic acid. So the same molecule, it is capable of donating 6 pair of electrons to the same metal atom. So EDTA is prefers to form the complex with say calcium or barium. So to the same central metal ion, either to the calcium or to the barium, say it is capable of or linking through 6 coordinate bonds. Okay, so now such complexes are said to be chelates. So chelates are the complexes which are having ring structure. When the bidentate reacts with the metal ion means, so the two lone pair of electrons are given by the same ligand to the metal ion. For example, in oxalate, there will be a formation of ring structure in the molecule. So the complexes having such a ring structure in the molecule, they are said to be chelates. Okay, and chelates are organometallic compounds. So now other examples for say ligands. DMG, dimethyl glyoxime, is also a chelating agent. Aluminum is also a chelating agent. Oxime, 8-hydroxyquinoline, is also, suppose say when it reacts with the magnesium, it gives the complex and that complex is having ring structure and that is said to be a chelate. Okay, so the polydentate ligands which are going to give the chelates are said to be chelating agents. Okay, so now with this we'll move on to the characteristics of chelates. See the first one, constituents lose their identity. That means the properties of the chelate is entirely different from the constituents from which it is formed. That means the properties of the constituents will be different from the properties of chelates. So thereby the constituents lose their identity after forming the complex or chelate. Second one, the second characteristic we can say donor atoms. So they link firmly with the metal ion through coordinate covalent bond. Okay. The third one, size of the metal ion. The size of the metal ion should be suitable in size, which is just fit to the position in the heterocyclic ring. That means in the ring structure. Okay. So now the third one is charge on the metal ion. So greater the charge, greater will be the attraction for the lone pair of electrons of the approaching ligand, and thereby say the complexes will be quite stable. Next, usually the number of, that means the member of ring size will be either 5-membered ring or 6-membered ring. So this is an example for 5-membered ring. So there are 5 bonds and it is said to be a 5-membered ring. Okay, and usually 5-membered rings are quite stable compared to 6-membered ring. Now the next criteria or the characteristic is say low, they usually possess low melting point or volatile in nature. Okay, now with this we'll move on to the next one, factors affecting the stability of chelate. First one is the ring size. So usually they form 5-membered or 6-membered ring. Out of this 5-membered ring structured molecules or complexes are quite stable. They are quite stable, and that is the angle between the bonds is found to be 108 degree, and according to angle strain theory, as per the angle strain theory in organic chemistry, the 5-membered rings are quite stable than 6-membered ring. Okay, so now number of rings, ring size it is. Second one is the number of rings. As the number of rings increases, the stability of the chelate increases. Then the resonance effect. So if the molecule fusses or exhibits the resonance, means it is quite stable. Then the steric effect. Okay, if the ligand are bulkier in size, then due to steric effect, the stability of the chelate may be decreased. Okay, then the next factor is basicity of the ligand. So basicity means what? Electron pair donating tendency. If the ligand is more basic in nature, that means it is more eager to, or it is more ready to, that means it is eager to, or it is having more tendency of donating the pair of electrons, then it is said to be having more basicity. So greater the basicity, stronger will be the bond, and chelate will be more stable. Okay, so basicity increases the stability of the resulting complex. So metal basicity of the metal, here it is reverse. So metal should have lesser basic nature. It should be ready to accept the electron than to lose the electron. It has to be eagerness to accept the pair of electrons and lesser tendency of losing or donating the electron, and that is said to be a basicity. And lesser the basicity of metal ion, greater will be the stability of the chelate. So next, the effect of substituents on the ligand. So there are some substituents may hinder the formation of a bond with the metal ion, thereby the stability decreases. Okay, so that is the effect. So now with this we'll move on to the next importance of chelates. See, the first one in the field of biological field. Say you are well familiar, hemoglobin, it is nothing but iron chelate, chlorophyll, it's nothing but magnesium chelate. And you know the role of either hemoglobin or chlorophyll in the biological system. Therefore, chelates are very, very important. Okay. Then the second one is in the analytical field. So, in analytical field, the chelates plays an important role. For example, in qualitative analysis, while detecting any element, for example, nickel. So, in the fourth sem, you have done the experiment. Say, to detect the presence of nickel in the given solution, if you add DMG, dimethyl glyoxime, in the ammoniacal medium to the nickel solution, so if it gives the red color PPT, indicates the presence of nickel. So like that, in qualitative analysis, one can detect the elements by using chelating agents which are going to form colored precipitate or colored compounds. Is it? So that is one of the greater benefit here. See, nickel DMG is used, or oxine for detection of magnesium ion, or aluminum reagent for the detection of aluminium, isn't it? So like that, chelates are used in qualitative analysis. So in the quantitative analysis, even in the quantitative analysis, either it may be gravimetric or volumetric, so they are used as a precipitating agent. So the same example we can take nickel. So by using DMG, one can estimate gravimetrically the amount of nickel present in the given solution. Okay. Similarly, say aluminium or magnesium, they can be estimated gravimetrically. Similarly, in volumetric analysis, many of the ligands, many of the chelating agents or the ligands are used as, say, indicators. For example, during the titration of calcium versus EDTA, where the erichrome black tea is used as an indicator, which is going to form a chelate, and that is colored chelate, thereby the endpoint can be determined. Similarly, ferroin indicator is used during the titration of iron versus potassium dichromate solution. Okay. Now the third one is chelates are used in, say, water softening. For example, EDTA, okay, it is used in industrial boilers. So in the boilers, due to hard water, there will be scales, formation of scales. That means deposition of say calcium or magnesium salts. Okay, so that can be removed when you add EDTA solution to the scales. When the scales are treated with EDTA solution, EDTA forms a chelate with calcium or magnesium, and that will be a soluble salt, and thereby the scales can be removed. So in industries it is used. Even for water purification they are used as a resins. Okay, next they are also used in removal of poisonous metals from the body. For example, say the toxic elements like lead, arsenic or mercury, if are present in the body, those elements can be removed by using chelating agents. Similarly, solvent extraction. In the solvent extraction, the chelating agents will form soluble salts, and thereby the required one can be extracted. And the food preservator, see the chelates are used as a food preservator. For example, EDTA, dilute solution of EDTA are used as a preservator in food like fruits or fruit juice or even foodstuffs, etc. Okay, so these are the say importance or the uses of chelates. Okay, with this we'll close today, and in the next class we'll start with the paper 2. Okay, thank you.